Okay, so today we're just going to take a brief look at 7.2, which is about series solutions of linear second order ODEs. Right, so every linear second order homogeneous ODE looks like some kind of P of x y prime prime plus Q of x y prime plus R of x y equals 0. And so far, we've only considered the case where P, Q, and R are in fact constants. That's when you can use the characteristic equation or the Laplace transform. But what if they're not constants? Well, in that case, you're dealing with a much harder situation. So there is a last resort that you can use, and that is trying to find a solution by power series. You see, that involves asserting a solution of the form y equals sum from n equals 0 to infinity of Cn x minus a to the n, and then trying to find, well, first of all, finding a, but more importantly, finding the constant Cn for each value of n. So let's talk about some examples of how to go about that. So we're going to start with an easy example that could be more easily handled by the characteristic equation, but it illustrates the method of how this works. So let's say we're starting with something really easy, like y prime prime minus y equals 0. Again, characteristic equation would be a much better way to do this, but we're just looking at this in order to illustrate how the method works. So what you've got to do is you've got to assert a solution, y equals n equals 0 to infinity, Cn x to the n. Okay, then we'll need two derivatives of that. The first derivative is going to be sum from n equals 1 to infinity, n Cn x to the n minus 1. By the way, the reason why it's n equals 1 to infinity now is because if n is 0, then this whole thing is just 0. And y prime prime is sum from n equals 2 to infinity, n minus 1, Cn x to the n minus 2. And again, it's n equals 2 to infinity because when n is 0 or 1, this whole thing is just 0. So it makes no difference whether you put n equals 0 or n equals 2. Okay? Now if this y is indeed a solution of this ODE right here, then in that case we can write down sum from n equals 2 to infinity, n minus 1, Cn x to the n minus 2, minus sum from n equals 0 to infinity, Cn x to the n. This has to be 0. Okay? Now, our goal is to find what Cn is for each value of n. And to do that, what we're going to have to do is say some power series equals 0, because then all the coefficients would be 0. Unfortunately, we do not have that right now. What we have right now is a power series minus another power series equals 0. So, in other words, what I'm saying is we'd like to combine like terms. There is a problem there. There is a problem there in that this x has n as its exponent, whereas this x has n minus 2 as its exponent. So what we have to do is a small change of variables. I'm going to define k to be n minus 2. And by the way, I'm only going to be working with this power series on the left-hand side. This one on the right, I'm going to leave alone. So k equals n minus 2. In that case, this becomes sum from k equals 0 to infinity, k plus 2, k plus 1, ck plus 2, x to the k. And then we still have this sum from n equals 0 to infinity, cn x to the n, and then this is still equal to 0. Now, let's understand that k, that if we were to write out the terms of this power series, well, it'd be an infinite sum, right? But more importantly, k would not appear in it. So if you write out the terms of this power series, you get 2 times 1 times c2 x to the 0 plus 3 times 2 times c3 x to the 1 plus 4 times 3 times c4 x to the 2 plus 5 times 4 times c5 x to the third plus dot dot dot. That would be a representation of this power series on the left, right? I mean, correct? Okay. So what I'm trying to emphasize is that the letter k does not appear in this entire expression. Why does the k appear here? Well, it's just a notational tool that helps us keep track of what term we're on. The truth is, this k means nothing. So if you replace it with n, no harm done. So this becomes sum from n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, x to the n, minus sum from n equals 0 to infinity, cn x to the n equals 0. And now we are able to combine some things together into a single power series. So we combine the like terms here. What we get is sum from n equals 0 to infinity, n plus 2, n plus 1, cn plus 2, minus cn times x to the n equals 0. Okay. So this is saying a power series is equal to 0. Well, there's only one way that that could happen, and that's if all of the coefficients are 0. So what that means is that we have all of these coefficients here for n greater than or equal to 0, n plus 2 times n plus 1 times cn plus 2 minus cn has to be 0. Okay? From there, we can say Cn plus 2 is going to be Cn divided by n plus 2 times n plus 1. This thing right here is called the recurrence relation. It's a relationship between all of the coefficients that tells us how to write down the solution of this ODE. So what we need to understand here is that we're dealing with a relation that describes a sequence. And so we just have to write down what the terms of that sequence actually are. And then write that sequence in closed form, that is, write it as a function of n, and then we'll be done. So, C0 is whatever C0 is, and C1 is whatever C1 is. But C2, that would be C0 divided by 2 times 1. So C2, that's C0 divided by 2 times 1. C3, that would be C1 divided by 3 times 2. C4, that would be C2 divided by 4 times 3, which ultimately we know C2 is C0 divided by 2 times 1, so this becomes C0 divided by 4 times 3 times 2 times 1. C5, we know that that's going to be C3 divided by 5 times 4. C3 is C1 over 3 times 2, so this becomes C1 over 5 times 4 times 3 times 2. C6 is going to be C4 divided by 6 times 5, which is just going to be C0 divided by 6, 5, 4, 3, 2, 1. C7 is going to be C5 divided by 7 times 6. So that's going to be C1 divided by 7, 6, 5, 4, 3, 2, and so on. Okay? So let's notice here, Cn is going to be something different depending on whether n is even or odd. If it's even, it's going to be C0 divided by n factorial. If it's odd, it's going to be C1 divided by n factorial. So this is if n is even and if n is odd. So now I'm going to erase this part on the left. If you need to see it, then I suggest pausing the video. Now that we have this closed form description of the sequence of coefficients, Cn, well, the solution by definition, we said was n equals 0 to infinity Cn x to the n. This, might I add, is the sum from n equals 0 to infinity Cn x to the n for even values of n, plus the sum from n equals 0 to infinity Cn x to the n for odd values of n. So let's see here. If n is even, then this is going to be sum from n equals 0 to infinity C0 over n factorial x to the n. So this is for even values of n. Then add to this sum from n equals 0 to infinity. The odd ones are going to be C1 over n factorial x to the n for odd values of n. Now, the first time I taught this class, I told my students that writing this as your final answer was not enough, that you needed to go further and rewrite this in a nicer notation, which you can do. You can rewrite this as sum from n equals 0 to infinity C0 over 2n factorial x to the 2n plus sum from n equals 1 to infinity, or actually n equals 0 to infinity, C1 over 2n plus 1 factorial x to the 2n plus 1 So the first time I taught this class, I told my students that they needed to write their solution like this. They couldn't write it like this. I have changed my mind. Now, if you write your final answer like this, where you say, just take the even terms here and just take the odd terms here, I'm all right with that. Okay? But in any case, this is how the method works. We propose y equals n equals 0 to infinity Cn x to the n, and we see what that implies for our ODE. We eventually get a power series equal to 0, and then that gives us that all the coefficients are 0, which gives us what we call the recurrence relation. That recurrence relation tells us about the sequence of coefficients, and 1, 2, 3, we have our general solution. If you're wondering where the arbitrary constants are, because this is a second order ODE and therefore we should have two arbitrary constants in the general solution, they're C0 and C1. So they're there. All right. Okay, so let's do some more examples. Since we're done with Laplace transforms, we will no longer need this table, so I'm going to erase it. Okay, let's suppose we're trying to find the general solution of the following ODE. X squared plus 1 times y prime prime plus, minus 4xy prime plus 6y equals 0. Now this, I just want to point out, is impossible to do by the characteristic equation. because the coefficients are not constant. Well, this one is, but the other ones aren't. It's also impossible to do by Laplace transform because Laplace transform methods also require that the coefficients be constants. Okay, so we use our last resort method, which is a power series. So y equals sum from n equals 0 to infinity, cn x to the n. In that case, y prime is going to be sum from n equals 1 to infinity, n cn x to the n minus 1. Y prime prime is going to be sum from n equals 2 to infinity, n minus 1, cn x to the n minus 2. And we put that information into the original ODE. So what we'll get here is x squared plus 1 times the sum from n equals 2 to infinity, n minus 1, cn x to the n minus 2. Subtract from this 4x times the sum from n equals 1 to infinity, n cn x to the n minus 1. Add to this 6 times the sum from n equals 0 to infinity, cn x to the n. This should all be 0. Okay, so let's distribute everything first. So what we'll get here is sum from n equals 2 to infinity, n minus 1, cn x to the n. Then add to this sum from n equals 2 to infinity, n minus 1, cn x to the n minus 2. Then minus sum from n equals 1 to infinity, 4 n cn x to the n. Then add sum from n equals 0 to infinity, 6 cn x to the n. And this is equal to 0. Okay, so now once again we'd like to combine like terms into a single power series that we can then say is equal to 0. Unfortunately, we have some problems here. First of all, this n minus 2, all the other exponents are n. So what we're going to have to do is that same change of variables as we did in the previous problem. We'll say k equals n minus 2, in which case this particular series becomes k equals 0 to infinity, k plus 2, k plus 1, ck plus 2, x to the k. Meanwhile, we still have these other terms, sum from n equals 2 to infinity, n minus 1, cn x to the n, and then minus sum from n equals 1 to infinity, 4n cn x to the n, and then plus sum from n equals 0 to infinity, 6 cn x to the n equals 0. Okay, so now replacing all these k's with n's, because again, it makes no difference. N equals 0 to infinity, n plus 2, n plus 1, cn plus 2, x to the n. We still have a little bit of a problem here. The problem is that these don't all start from the same index of n. Okay, this one starts from n equals 0, this one starts from n equals 1, this one starts from n equals 0, this one starts from n equals 2. So what we've got to do is separate out the terms that are not present in the other power series. So these two have terms for when n equals 0. The rest of them do not. So I'll have to separate those terms out. So we just take this and say, all right, n equals 0. So that gives us 2 times 1 times c2 x to the 0. Then add to this 6 times c0 x to the 0. All right. Now, these terms, these last three terms have n equals 1 terms. So we're going to have to separate those out because those are not present in the first series terms. So we're going to have here 3 times 2 times c3 x to the 1 minus 4 times 1 times c1 x to the 1 plus 6 c1 x to the 1. And now the rest of the stuff is all n equals 2 to infinity, so that's present everywhere in these series. And therefore we can just add them together now. So we get sum from n equals 2 to infinity n minus 1 cn plus n plus 2 n plus 1 cn plus 2 minus 4n cn plus 6cn times x to the n. This all equals 0. It's a long equation, huh? But in any case, what this tells us is that we now have a power series equaling 0, so therefore all of its coefficients are 0. So we get here, first of all, that 2c2 plus 6c0 is equal to 0. We get 6c3 minus 4c1 plus 6c1 is equal to 0. And for n greater than or equal to 2, we get n times n minus 1 times cn plus n plus 2, n plus 1, cn plus 2, minus 4n cn plus 6cn equals 0. Okay? And then this infinitely large system of equations is what we call our recurrence relation. So we have 1, 2, and then infinitely many for each integer greater than or equal to 2. All right, so now the rest of the problem is just trying to figure out what this thing is by analyzing the sequence of coefficients Cn. So I'm going to erase some stuff. If you need it, then I would suggest pausing the video. All we need from here on is this, the recurrence relation, and what our solution is supposed to be. So, first of all, you can divide this whole equation by 2 and get C2 plus 3C0 equals 0. you can add up these two terms here to get 6C3 plus 2C1 equals 0. And then you can divide that equation by 2 to get 3C3 plus 1C1 equals 0. As for this equation, we have some like terms, or, well, these equations, I should say. We have some like terms that we can combine. We can say that this is for n greater than or equal to 2. We have n squared minus n times cn plus n plus 2 times n plus 1 times cn plus 2. Then plus 6 minus 4n cn equals 0. We have these like terms that we can combine. So what we'll get here is n squared minus 5n plus 6 cn plus n plus 2 times n plus 1 cn plus 2 equals 0. This gives us n minus 2, n minus 3 cn plus n plus 2, n plus 1 cn plus 2 equals 0. And therefore cn plus 2 equals negative n minus 2, n minus 3 divided by n plus 2, n plus 1 times cn. And now we no longer need the raw form of the recurrence relation. Okay, so let's write out a few terms of this sequence. First of all, C2 is negative 3 times C0. C0 is whatever C0 is. C3, C1 is whatever C1 is. C3 is going to be negative 1/3 times C1. And now C4, let's write that down, C4 is going to be negative 0 times some stuff times C2. But of course, 0 times anything is 0. Then C5 is going to be when n is 3. So this is negative 1 times 0 times some more stuff. But of course, since you have a 0 in there, this whole thing is just going to be 0. C6, according to our recurrence relation, that's going to be something times C4. C4 is 0, so C6 is 0. C7, according to our recurrence relation, that's going to be something times C5. C5 is 0, so C7 is going to be 0. And then C8 is 0, and C10 is 0, and so on. And C9 is 0, and C11 is 0, and so on. So what we get is all the coefficients are 0 except C0, C2, C1, and C3. Okay? So, y, the solution, this is going to be the sum from n equals 0 to infinity, Cn x to the n for all of the even terms, plus sum from n equals 0 to infinity, Cn x to the n for all of the odd terms. When n is even, this is going to turn into C0 times x to the 0 minus 3C0 times x to the 2, and then the rest is 0. Then over here we have plus, okay, C1 times x to the 1 minus 1/3 C1 times x to the 3rd. And then everything else is 0. So then, this is the general solution of our ODE. Okay? Let's do another example. X squared minus 3. Actually, no. I want to do the example after that one. So, y prime prime plus 2xy prime plus 4y equals 0. Once again, you couldn't do this by any of the methods that we saw before today, because this coefficient right here is not constant. So we'll do it by power series methods. We'll write down y equals sum from n equals 0 to infinity, Cn x to the n, in which case y prime is sum from n equals 1 to infinity, n Cn x to the n minus 1, and y prime prime is the sum from n equals 2 to infinity, n minus 1 Cn x to the n minus 2. You put that information into the original ODE, and what you'll get is sum from n equals 2 to infinity, n minus 1, Cn x to the n minus 2, plus 2x times sum from n equals 1 to infinity, n Cn x to the n minus 1, plus 4 times the sum from n equals 0 to infinity, Cn x to the n. This is all equal to 0. We can distribute. What we'll get is sum from n equals 2 to infinity, n minus 1, Cn x to the n minus 2, plus sum from n equals 1 to infinity, 2 n Cn x to the n, plus sum from n equals 0 to infinity, 4 Cn x to the n equals 0. So now, once again, we have a problem because this exponent is not the same as these two exponents. So we'll do our change of variables. K equals n minus 2, in which case this first term becomes k equals 0 to infinity, k plus 2, k plus 1, ck plus 2, x to the k. And then the rest of these remain the same. So sum from n equals 1 to infinity, 2n cn x to the n, plus sum from n equals 0 to infinity, 4 cn x to the n, this equals 0. So now, again, let's replace all these k's with n's because it makes no difference whatsoever what we call the index. So now we can, well, we can combine some like terms, but we have to note that these have different starting positions for the index. So we'll take out the n equals 0 terms first. This will become 2 times 1 times c2 x to the 0 plus 4c0 x to the 0. And then the rest of this we can combine. So n equals 1 to infinity, n plus 2, n plus 1, cn plus 2, plus 2 n cn plus 4 cn x to the n equals 0. So at this point, we have a power series is equal to 0, so that means all of its coefficients are 0, which means 2c2 plus 4c0 equals 0. And for n greater than or equal to 1, n plus 2 times n plus 1 times cn plus 2 plus 2n cn plus 4cn equals 0. And then this infinitely large system of equations is our recurrence relation. That's all we need at this point, so I'm going to erase everything else. If you need to see everything else, then I suggest you pause the video. So, first of all, we can rewrite the first equation as C2 equals negative 2C0, of course. Besides that, we have some like terms that we can combine in the infinite part. So n plus 1 times n plus 2 times cn plus 2. Add to this 2n plus 4, which is, by the way, 2 times n plus 2. Cn equals 0. We can cancel the n plus 2. And then what we have is Cn plus 2 equals negative 2 divided by n plus 1 times Cn for n greater than or equal to 1. Okay. So once again, C0 is whatever C0 is, and C1 is going to become whatever C1 is. These are going to become the arbitrary constants in our general solution. C2 is apparently negative 2 times C0. Then C3, that's when n equals 1 in this equation. C3 is going to be negative 2 over 2 times C1. So C3 is going to equal negative C1. C4 is going to be when n is 2 in this equation, so that's negative 2/3 times C2, which in our case is going to be negative 4 over 3 times C0. Then C5 is going to be negative 2 over 4 C3, so negative 1/2 of C3, which is positive 1/2 of C1. C6 is going to be, when n equals 4 in this equation, negative 2/5 times C4, which is just going to be negative 8 over 15 times C0. Then C7 is going to be when n is 5 in this equation, so negative 2 over 6, so negative 1/3 times C5, which is just going to be negative 1 over 6 times C1. And you can keep going like this. So for this problem, I'm going to write the answer in a slightly different notation. You see, we can write this as n equals 0 to infinity Cn x to the n, for n being even, plus sum from n equals 0 to infinity Cn x to the n, for n being odd. When n is even, we're looking at this left column. So that's going to be C0 x to the 0 minus 2C0 x squared minus 4/3 C0 x to the 4th minus 8/15 C0 x to the 6th plus, or minus actually, dot dot dot. Those are all the even terms. And then the odd terms, let's see, we're going to have C1 x to the 1 minus C1 x to the 3rd plus 1/2 C1 x to the 5th minus 1/6 C1 x to the 7th, then plus dot dot dot. And then this is a perfectly valid way of writing the general solution of our ODE. Okay? So it may be complicated. It is complicated. But let's understand the anatomy of how these methods always work. You always take y to be n equals 0 to infinity, cn x to the n. Then from there you take a couple of derivatives and put that into the original ODE. From there you're going to get a power series that is equal to 0. That gives you that all the coefficients are 0, which gives you the recurrence relation. And then using that recurrence relation, you can study the sequence of coefficients of y. And that's how we do it. Okay? So, that's all for today. See you in the next one.